Okay, we are live. Morning. We have some stuff to do today. So I think that we're just going to optimize the heck out of training today in Puffer. We're going to check on our experiments we ran overnight first, though. We got to check on those. There's one thing I want to check on first, which is just the this run versus the previous run. I want to check on the sample complexity, just so that we know whether our new algorithm is performing as well as we think it should be able to. Okay, so this is the one that we had where it's like really, really good, right? It's gamma, lambda, and then if we look here, lambda's all over the place, gamma's whatever, because it doesn't matter in this this version. But what we want to look at is the charts. So here we have why are all of these experiments running so long? Shouldn't be, right? Hang on, are these all... These are all at like 100K. And... something very weird there. Or 100 mil. These ones... I mean, we also have, clearly, we have 50 mil solves for this one as well. Right, this is a 50 mil solve right here. Now it does look like we have a few somewhat faster solves over here. Mind you, we haven't finished the other sweep yet. It's weird that they're all out to 100 mil though. Right? They shouldn't all be up to 100 mil. I don't know why they would be. What end? This is breakout. So this is our completed sweep over breakout. And you can see we have solves in a minute and a half and almost solved in, this is under 2 minutes. So this one is very good. This is just PPOJE. But it's weird how the total time steps is locked to 100 million up top, right? Like, I don't know how it's this fast at 100 mil. We had a cost graph, didn't we? Yeah, we do have a cost graph. So kind of want to see this one. 21002. See, this one is reasonable. This one is not 100 mil. Maybe this one. Yeah, it's this one here. But I don't know why there's so many samples all the way up here. It's doing something, clearly. Then we have I mean, we have pretty darn good solves with the other algorithm as well, the new algorithm. I suppose the question is going to be whether the new one is just not dialed into the level of the other experiments, or if there is a gap. We'll have to look at. I mean, it's very close at this point. It is very close. Well, we'll let the sweep run before we pass final judgment here. So I want to do something a little different today. I want to just work on some optimization for at least a little bit. So this is a cleaned up, a faster version of CleanRL that's like 6 times faster. I think we're 5 times faster than this already, but there's some things in here that we haven't done. Let's see. There are a few new things here from Vincent. Well, this is obvious. Reason for this stream series? I just stream my dev day-to-day on PufferLib. My goal is to fix reinforcement learning. I want to make everything fast and stable. We've made a ton of progress on this as well. So if you just go to puffer.ai, you can see we have a dozen different environments here, from very simple stuff like Breakout to very complex like this mini MMO. And all of these things that you're seeing are agents just playing the game, trained with reinforcement learning, some of them being superhuman. So we are trying to make really fast environments and really good tools to make it easy to do reinforcement learning very fast. So at the moment, I think we're going to be doing today some optimization on the training side of the current library. It's already very fast, but I want to see if there's any more performance that we can eke out of it. Interesting. That's silly. So let's see if they found anything useful in lean RL here. Let me load the chat as well so I can deal with that if I need to. I think when I talked with Vincent, I think he understood shared memory correctly. Let me see. So I want to create a CPU tensor in PyTorch. Content of this tensor needs to be placed in memory. We distinguish two types of memory, the RAM and the swap space. Together, these make a virtual memory. Okay, but you should never be doing that, right? You should never be swapping to disk anyways. Regular CPU tensor is pageable, which means it's divided in blocks called pages that can live anywhere in the virtual memory, both in RAM or on disk, but they're going to stay on RAM. Memory seems larger, okay? When program accesses a page that's not in RAM, page fault occurs, and OS brings this back into RAM. Okay, this is all irrelevant. This should never happen in RL. A pinned memory is a type of memory that cannot be swapped out to disk. Okay, good. So this is just telling the OS not to swap the memory. It's kind of weird to me that it would swap out the memory in the first place when you still have plenty of RAM. Memory is page locked. The device can access the memory directly in the main memory. If the memory is pageable, all pages will have to be brought to the main memory before being sent to the GPU. CUDA sends pageable data from CPU to GPU. It must first create a page lock copy of that data before making the transfer. Okay, so this is interesting. So when CUDA sends pageable data from CPU to GPU, it must first create a page-locked copy of that data. Asynchronous versus synchronous. When executing a copy from a host device, the CUDA toolkit offers modalities to do these operations synchronously or asynchronously with respect to the host. In practice, when calling to, PyTorch always makes a call to CUDA memcopy async. If non-blocking is false, a CUDA stream synchronized will be called after each and every CUDA memcopy async. Okay. If non-blocking is true, then no synchronization is triggered, and the main thread on the host is not blocked. So multiple tensors can be sent to the device simultaneously, as the thread does not have to wait for one transfer to be completed to initiate the other. So this is important. In general, the transfer is blocking on the device side, even if it isn't on the host side. The copy on the device cannot occur while another operation is executed. However, in some advanced scenarios, a copy and kernel execution can be done simultaneously on the GPU side. 3 requirements must be met to enable this. The device must have at least one free direct memory access engine. Modern GPU architectures have more than one. The transfer must be done on a separate, non-default CUDA stream. In PyTorch, CUDA streams can be handled using stream. The source data must be pinned to memory. Demonstrate this by running profiles on the following scripts. So, okay, there's some good stuff here. So you have a stream. You have pinned and non-pinned tensors. And then we have a CUDA tensor. This is just a perf test. And then, oh, I didn't know that these nice profiles were there. Cool. We will probably be using this later today in profiling PufferLib. Using a pinned memory tensor doesn't change the trace much. Both operations are still executed consecutively. Can we see this? Let's go to review mode. I also want to work in RL and do research in it myself, but I don't have a good laptop with GPU for training. Only have Core i7. Suggest me what I should do. Some of Puffer's environments are so fast that you can kind of do training on our environments on CPU faster than the majority of researchers can do on GPU. So if you just want to like get into it a little bit and train some stuff and not have it take forever, you can probably still train a few of our environments in, maybe it takes 5-10 minutes. Like our stuff is really fast. You probably can still do training at like 100,000 steps per second for Breakout or Pong. For context, on a modern core, each of these environments runs at 1,000,000 steps per second. We use the GPU to get 300,000 to 1,000,000 steps per second training, but for the smaller models, you can often still train at 100K just on like even on just a core. And give that a try. I also have a quick start guide on the website that I highly, highly recommend. I mean, I literally wrote it for people who want an easy way to get into RL. So let's go to blog, quick start guide. It's like a 20-minute read, links you to some other resources. Can we see what this image is? Okay, cool. So now we can see this. And I actually should go back to here so we can see it properly. Okay, atten 2 copy, and then we can see that this little gap here, this is the overhead of whatever the PyTorch binding is, and this is the whole CUDA mem copy. Okay, so this is the first one, 9199 microseconds. And here's the synchronize. Okay. Sending a pageable tensor to GPU on a separate stream is also a blocking operation. Streamed equals true. Only pinned tensor copies to GPU on a separate stream overlap with another CUDA kernel executed on the mainstream. Okay. on a separate stream though. So how do you use this stream thing? With torch CUDA stream S. You have to manually manage these things. That's annoying. Okay, but it's not that hard to deal with. Where did we go? PyTorch perspective, pin memory. PyTorch offers the possibility to create and send tensors to page lock memory through the pin memory method and constructor arguments. CPU tensors on a machine where CUDA is initialized can be cast to pin memory through the pin memory method. Pin memory is blocking on the main thread of the host. It waits for the tensor to be copied to page lock memory. Yeah, you should never be doing pin memory in a loop or something anyways. That's dumb. New tensors can be created in pin memory with functions like zeros, ones, and other constructors. Let's check the speed of pinning memory and sending tensors to CUDA. Pageable tensor dot pin memory dot to device. Yeah, so this is stupid. If you're doing this, you don't know what you're doing. Pageable tensor dot to device, the baseline, and then you save 20% if it is pinned. Cool. So, contrary to a somewhat common belief, calling pin memory on a pageable tensor before casting to GPU should not bring any significant speed up and should be slower. Okay, yeah. If you're doing this, you just don't understand your hardware. Yo, how's it going, Spencer? We're going to perf optimize the crap out of Puffer today. We're going to see if we can hit 2 million trained SPS on something. I just haven't done this in many months, so I figure I'd take a day to do it. Unblocking is true, okay. To account accurately of the benefit of using unblocking, we'll design a slightly more complex experiment since we will want to assess how fast it is to send multiple tensors to GPU with and without calling non-blocking. Okay. 25. Okay, so it's not magic. You know, there's like 20-25% overhead sometimes with synchronization. To get a better sense of what is happening here, feeling pretty confident on the portability of GPU drive, only got one more thing to clarify with how the dataset gets loaded and should be clear. Great. I went to Brendan's defense yesterday. Brendan is the author of Madrona. We'll see if he has ideas on GPU drive for the Madrona version, but I think regardless that our CPU version is just going to be awesome to have. Because regardless, right, it will make the project faster, even if they get it to work in Madrona. Ours will run on web, which theirs will not, right? Ours will be easier to use because it won't require all the C++ shenanigans. And this is also an opportunity for us to figure out variable agent stuff in C, which will then let us make a whole new class of environments. And also, I think that in the process of doing this, you're probably going to have to do stuff like go look at Madrona's bounding volume hierarchy thing, which is how they handle lots of entities in 3D. And that will be an amazing piece to have for Puffer in C. So I think we can just use some of those things and like port them to C, and then we'll have way, way, way more flexibility with working with all sorts of 3D environments in the future. So I think that you're like, if this is the type of stuff you're interested in, yeah, this is really going to be at the frontier of how do we make fast M's work. I got to chat with Brennan actually on what he's planning to do going forward because he's got some cool tech. Some really exciting ways to expand the amp. Oh yeah, lots of them. Definitely. It's kind of funny. I realized watching Brendan's defense yesterday that like the stuff he's doing is way, way, way more sophisticated than what I'm doing with PufferLib, right? He's written like a CUDA game engine, basically. But the stuff that we're doing is like so much more flexible, and it's still fast for so many different domains, and it's so much easier to do, right? So I don't know. There are definitely things that we cannot do that he can do with his approach that I want to think about. Like we've never tried software rendering, for instance. I don't know how fast we could get like a pixel rendering done if we wanted to. Though technically, to be fair, we could take. I think we could just use their batch renderer. So we could because it like renders from a data format that's very similar to what we have. So technically, we could still write the whole sim on CPU and then just render on GPU. I think that would still work. So I don't know. You can have every trajectory in the end be a controllable agent. If you could port a map of LA or something, then randomly set goals of a shit ton of cars. Yeah, no, you could definitely. I mean, if you want to make, you're basically making hyperf GTA at that point. It'd be sick. Yeah, we'd be happy to have that. That'd be cool. That would be awesome. You just have to evaluate how hard individual things are, right? And what corners to cut and stuff like that. Profile memory. What are we looking at here? Welcome, YouTube folks. Today is going to be optimizing the crap out of PufferLib all day. We're going to try to hit 2 million steps per second training on some of our environments. That's going to be the goal. I don't know if it's even possible, but we're going to try it. I'm currently going through this blog post from Vincent on LeanRL, which is an optimized version of CleanRL that's like 5 or 6 times faster. PufferLib is already 5 times faster than this, but I don't think we're using all the same optimizations. So there might still be stuff in here. First start with port. Look into bounding volume hierarchy stuff. It's necessary for a bunch of 3D collisions. Yeah, they have stuff for collisions in there. Now, I don't know if the way that they do it is actually going to be the best way to do it, right? There are a lot of different ways that you can do that type of stuff. So you have to look at if the way that they have it makes sense. Let's start with, let's see the call stack with a regular .to device first. Call to device, profile memory, copy to device tensors. This says huh? So there's a whole bunch of garbage here. To copy, empty strided. I don't know what any of that is. I still don't know if it's more efficient to try to emulate the physics with a good model to train an RL-based model. Wait. I still don't know if it's more efficient to try to emulate the physics with a good model to train an RL-based model. They have really low compute fluid models. 2-minute papers talked about this years ago. I don't know about any of that stuff. Non-blocking version. Call to device. Profile memory. And now, I don't know what all these functions are though. Empty strided. To copy, copy. Like, what the heck, right? Better when using non-blocking true, as all transfers are initiated simultaneously. So this is 23 ms, 31 ms, okay. Synergies. Now that we've made the point that data transfers of tensors already in pin memory to GPU is faster, and that we know that doing these transfers asynchronously is faster than synchronously, we can benchmark the combination of these approaches. First, let's write a couple of new functions that we'll call pin memory and toDevice on each tensor. Oh yeah, also, one thing I've been wondering, guys, just for this stream, does the mic sound substantially better if I move it closer? Like if I do this, is this substantially better? Now that we've made the point, the data transfers, okay, so I'll look into this. I think I thought of a way to update on every simulation run just by running multi-agency framework to change circuit parameters and get rid of bad sims quickly. That'd be cool. Yeah, anything you can do to make sim faster is usually really helpful in RL. We can benchmark the combination of these approaches. Okay, so pin plus async. Pin memory are more pronounced for somewhat large batches of large tensors. Okay, so this is a very, very optimistic benchmark. Okay, so it can be 2 or 3 times faster in a very optimistic case here. Favorite RL benchmark right now? Benchmark, all the benchmarks suck. All the benchmarks really suck. At the moment, what we're doing is we're just kind of using our environments in PufferLib as they are in their current form. So PufferLib, we're not providing our M's as like a stable benchmark, right? Like we will keep updating them and we will keep fixing bugs, and we're not doing historical versioning and all sorts of shenanigans. The idea is that at any point in time, if you have two methods, right, that you want to compare, you just train them both on our environments and you see what you get. And the training is so fast that you can do that. You know, you can do that, and we don't really need to have like an old historical copy. But yeah, PufferLib RMs are what we're using. We will be doing like some external runs, I'd say, on like Atari and ProcGen and stuff, but we're not going to do optimization. Like we're not going to do hyperparameter sweeps, I don't think, anymore over original Atari or ProcGen. It's just you're wasting compute. It's so bloody slow. Until now, we've operated under the assumption that asynchronous copies from the CPU to the GPU are safe. What? This is generally true because CUDA automatically handles synchronization to ensure that data is being accessed is valid at read time whenever the tensor is in pageable memory. In other cases, we cannot make the same assumption. When a tensor is placed in pin memory, mutating the original copy after calling the host to device transfer may corrupt the data received on GPU. When a transfer is achieved in the opposite direction, there's no guarantee that the data read on GPU is valid without explicit synchronization. What? In these scenarios, the transfers offer no assurance that the copy will be complete at the time of data access. Consequently, the data on the host might be incomplete or incorrect. Let's demonstrate this with a pin to memory. So if you create a pin memory tensor, you send the tensor to CUDA, it doesn't complete, then you corrupt the original tensor. That is incredibly stupid. This thing should have a flag set that tells you that it's being used or something. That's weird. Using a pageable tensor always works. All right, this is Vincent. Instead of writing a blog post on this, fix it in PyTorch, please. This should not happen. Let's demonstrate that CUDA to CPU also fails to produce reliable outputs without synchronization. You know, it's so weird when you have like some big, like Python front end framework. You kind of expect everything to work and not fail in weird ways. Like, this is the type of stuff that's allowed to happen if I'm working in C, right? Because I expect that type of stuff to happen, and I'm not gonna like this is the type of thing that you would get stuck on for hours because you wouldn't expect this to be possible in something where you check it way earlier. If this were like a C++ front end or something, you just check it way earlier and assume that something could be screwy. CUDA to CPU also fails to produce reliable outputs. Asynchronous copies to a device are safe without explicit synchronization only when the target is a CUDA-enabled device and the original tensor is in pageable memory. Great. In general, non-blocking is true, will be good throughout, will provide good throughput. If tensor is already in pinned memory, transfer can be accelerated. Sending it to pinned memory manually from Python main thread is a blocking operation on the host, and hence will annihilate much of the benefit of using non-blocking equals true. One might now legitimately ask what use there is for pinned memory method. In the following section, we'll explain how this can be used to accelerate the data transfer even more. PyTorch notoriously provides a data loader class whose constructor accepts a pin memory argument. Considering our previous discussion on pin memory, you might wonder how data loader manages to accelerate data transfers if memory pinning is inherently blocking. The key lies in the data loader's use of a separate thread to handle the data from pageable to pinned memory, thus preventing any blockage in the main thread. To illustrate this, we'll use TensorDict primitive from the whole. I didn't realize there was a adjective form of homonym. Homonymous? Homonymous. That's very weird. All right. I didn't know that. I learned a new form of a word today. In invoking 2, the default behavior is to send tensors to the device asynchronously, followed by a single call to torch device synchronize afterwards. Is this actually a word? This is bothering me. Huh, that is. I didn't realize there was an adjective form of that. That's funny. Invoking 2, default behavior is to send tensors to the device asynchronously, followed by a single call to torch device synchronize afterwards. Okay. TensorDict.2 includes a non-blocking pin option, which initiates multiple threads to execute pin memory before proceeding with .2 device. Yeah, we would not do that though. Oh, that is kind of interesting, to be fair. What are you linking me? That's funny. See, the question is at which of these layers can you do work quickly enough? Like, what is the furthest layer back that you can do work quickly enough to build massive things solo efficiently? And I think the line is right about here with maybe a little bit of assembly. Good RL agent for assembly. Actually, to be fair, it might be easier than for normal code agents. Non-blocking pin. Okay, so this is all TensorDict stuff. Again, this is the optimal case for TensorDict. No one-size-fits-all solution. So you need to have number of available cores, memory, CUDA device. Okay, cool. Nice blog post. So don't send tensors with .2 if you can instantiate them. Avoid pinning memory unless you thoroughly test it. Well, that's just the don't pin and then .2. Avoid calling tensor.item in between CUDA operations. This triggers CUDA synchronization and blocks your code. Delogging after all code has been completed. See how to find sync points here. Okay, cool. Avoid frequent calls to eval or train in eager mode. We don't do that. Avoid calling args.attribute often in the code. Wait, what? Avoid calling args.attribute often in the code, especially with Hydra. What? Avoid calling args.attribute, especially with Hydra. Is Python config, are like Python config libraries so bad that that is slow? That's obscene. That's like actually disgusting. In-place operations are not preferable to regular ones. Don't load your code if not absolutely necessary. Interesting. Very nice. Now, that's only one of the things here. There's also compile. CUDA graphs. Capturing the operations executed on a CUDA device using device buffers and replaying the same operations later. The graphs buffers are updated in place, new results can be generated. Here's how a typical CUDA graph pipeline appears. Interesting. With torch.cuda.graph, look for calls to torch compile and CUDA graph module within the _torch compile scripts. So PyTorch implementation, then leanRL implementation, then compile does nothing, but then compiled with coup de grace doubles it. Did he get this to work with LSTMs? Aha! I don't think he did. Is there an LSTM in here? There's not an LSTM in here. He didn't get it working with LSTMs. That is painful. I might be able to get the forward pass working with LSTMs. Let's see what he did here. So the switch statistics, here's your agent, it's JE, torch, compiler, coup de grace, mark, step, begin. Torch, compiler, coup de grace, mark, step, begin. And he doesn't mark the end, so assumedly it's at the bottom. It just marks step begin, there's no end. Coup de grace module here. So mark step begin, roll out. Mark step begin. Interesting. Now the question I'm going to have is how much time does this add to your launch? Right? Well, we will start with this. Okay. And we forgot to do dev branch has a couple things we're still experimenting with. I'm just going to get this to run and then I got to go do a thing real quick. And then I will be back in a few minutes and we will continue here. Okay, so current version is 900K train. Update epochs. This mini batch size is too small though. I mean, too big. Okay, apparently not. Cool. So we will start with there. That's the starting point, and I will be back in a few, and we will optimize. One sec. Okay. So, first thing I want to figure out, I thought that this thing could train at 1.2 million, though maybe that was just breakout. I think this one got up to about 1 million with optimal settings. Let me see. So, multiprocessing. Oh yeah, this is a very different environment, isn't it? That we have here. I don't see why it would be different though. This is 4096 of the same env. We could do Plong or Breakout instead, but I think this is probably fine. Should probably be fine. Yeah, okay, let's profile this one. We'll profile this one. This tells you all the PyTorch operations. This looks like what we want for profiling, right? So right here. Do with dot profile. Oops. Profile. Where did this with profile come from? Is this just torch.profile? Yeah, there we go. Where's this frickin' activities thing come from now? So we do this. Okay. Where's this trace handler? Export Chrome trace. Okay. Cool. Let's see if we actually can get some graphs out of this thing. This is going to be too long, obviously. 10 mil? 10 mil should be good. And let's see if this profiles. Okay, it's printing stuff, but it's all messed up. It's printing stuff and it's crushing my perf to the point that I don't even trust what it's profiling anymore. This thing is saying that there's 3x time spent in CPU versus CUDA, but it's also crushing my perf with the profiling overhead, so who knows? That's the problem with a lot of these profilers. We can see here the actual backward passes look like they don't take up any time at all. So we have, how do we get some stats out of this thing? So this literally just gives you device synchronize, which doesn't help. Maybe we have traces though. We do have traces. Cool. Export Chrome trace. And then you can examine so apparently we can take these files. Let's take like, I don't know, trace 8. Give it a little time to warm up. Trace 12. Can I just drag this in here? This. Cool. So we can actually look at these. I'm going to do this. Profiler step 10. How's this UI work? What do I do? I do not know how this UI works. Should be this thing, right? Okay, I actually don't know what the hell's going on with this thing. How do you zoom on this thing? Ah, very intuitive. Alt plus mouse wheel. Very intuitive. But we can see the profiles here, I think. We'll make sure we get the full thing. These all are very similar. You just get, oh. Okay, so this is all idle in here for some reason. What the heck do we do with this? Why do we have idle, like, big idle blocks? So here's the launches, the kernel launches. So we can see the launches here are a big chunk of perf. Okay. A10 multinomial. I can see the multinomial here is expensive. It doesn't really give me any information though on what to pursue now, does it? Let me try something else. I had a different profile I could try. That doesn't give me much information at all. Are you profiling? I don't think I have torch 2.6 right now. Oh no, I am. I have torch 2.6. I haven't seen any difference at all, by the way. I haven't seen any difference in perf. Okay, so there we have profile. Yeah, this is way lighter weight. Sampling multi-discrete. Yeah, that seems like a bug with torch or something. So we have 49% time spent in forward. %13% missed, 10% missed here. I think what we should do here that will be much more useful than this is to just expand on our built-in profiling. Except it is nice to have the summary. Well, I can always just expand it for now, right? And then I can format this cleanly later. If you could add, that's what I'm doing right now. I don't know why I have this done with yields like this. This is kind of insane. We'll rewrite a few things in here. So this should run immediately, right? Yeah, that runs. Cool. Let's do this. Eval copy. Training should be entirely on device, but let me just run this to just get an initial test. Okay, there we can see copies at 1%, but it's not synchronized. Man, hey, welcome. When was that reward clamping added? Fairly recently. It was needed for breakout. Like breakout just didn't work without it, so we just added it generally to the dev branch. Okay, so that takes a little bit off of MISC. Store is also copy, isn't it? Oh, this is all copying. This is all copying. I think what we get to do is we do this, and then we do this. Goes at the bottom. Now we get a different story, right? Now we get a different story. Okay. And as for train, MISC. Sort training data. Oh yeah. There's some overhead. So what can we do about it? This is, yeah, these indices are weird. I think before we optimize, we should make sure we actually have all the profiling that we want. What other profile? I don't necessarily know we need more metrics, but I want to make sure everything's classified correctly and every line's profiled. In-place update should be faster. This is an in-place update. Should be using a CUDA tensor to index. That's true. Sample logits. It's fine. I mean, we're gonna have to clean all this shit up a whole bunch, I'm sure. So, I think I put too much under eval copy, didn't I? Well, hang on, this is eval forward. Hold on, this is quite significant, right? 28, 29. Oh yeah. Uh-oh. 11K SPS. How's that happen? Hmm. Isn't there a thing where like indexing with CUDA tensor is slow? Oh, that's actually probably a big one right here, is this indexing. Yeah, this definitely needs to be special cased. So returning these indices is going to make it slower, for sure. Now, I would like to figure out first the indexing problem. So we definitely have clear actionable stuff that we can improve on this today. Definitely. In fact, I think this should be quite major. It's a CUDA tensor, right? It's a list. And this is slow, so for some reason this is slow. Very slow. This is still slow, but less slow. And then this is fast. Uh-huh. Well, let's see where this thing gets used. It gets used, it does get put in store. So if I just do, let's just do, CUDA NVID tensor. Okay, so this is just going to be, we're not using E3B, we're not going to worry about that. This is going to be CUDA NVID, CUDA NVID, and then we'll use it here. CUDA. Does that do anything? That immediately speeds us up to over 1 million FPS, 1.1 million. So this does something. Cool. We are definitely going to be able to make this library much faster. I know people are starting to creep up to Puffer in performance a little bit. No, Puffer will be fastest. In fact, I think that's a good enough result to tweet to get some people to join to stream to watch this stuff, because this will be fun. I'm gonna go grab a drink at least before I tweet that one sec. Okay. I'm very happy with that. But I don't understand what it is that's screwing this up elsewhere. So if I put this, whoops, let's use P3O. We're not using P3O. So if I put this in here, it's slow, right? Yeah. Holy. Yeah, that's very slow. Okay. Ah, that's it right there. It gets used for sort keys only. So, yeah, this is taking a lot of little slices of a CUDA tensor. So then this one actually shouldn't be the CUDA one. where mask numpy values mean.cpu. Okay, so what is our new overhead after that? Still at 20% copy overhead in eval. Not good. Okay. Next thing I can do here. Man, that's going to be tricky, actually, I think. Indexing is going to be fundamentally slower than slicing. Well, let's at least first see how much we're losing, because I think we are losing a lot, but we should probably confirm. To explain what's going on here, these envites are a list, and anytime you index with a list, you have to copy. So there's redundant copy going on here because of this. But I think we can get around it if we are a little clever. I think so, at least. Yeah, so just to start with, there's slice tensor. Maybe you don't need it. We can just do hi there, I've been doing research in RL for about 5 years now, and I just recently came across PufferLib. I respect all your work on trying to improve the experience with experimenting with RL. Thank you. Yeah, we are going to make RL way, way, way faster and easier. I think this year you're going to see it just become way easier to get RL working on new problems. We have a whole bunch of active open source efforts on this right now. If you're interested in getting involved, join the Discord. We have a lot of open projects right now. Research side, engineering side, lots of cool stuff. Right now, I'm trying to optimize our training loop. I found some overhead, so I think we're going to get this to be at least a good 20% faster today, maybe more. slice object. Right, so that's an issue. That got us 5%. I was expecting more. Oh, because of this mask. What are up today? What are you up to today? I'm perf optimizing PufferLib. We're gonna make training faster. There's overhead right now in the training loop that's caused by some of the fancy indexing we have to do. But I think we can optimize it in many cases. I'm just playing around at the moment to see how much overhead there actually is. I've already found a good 20% though that we can definitely fix. Still all this copy overhead, really? There should not be this much. Let me see. This is already on CUDA. All right, we're gonna add a thing to profile, so it's easier for me to see what's going on here. We're gonna just add custom. Just add custom at the bottom. Okay, and then now I can actually profile stuff as I please. We get 15% of time in copy. Let's do width file.custom. All this mess of logging you're seeing is obviously we're not going to leave the code looking like this. This is just me trying to quickly profile some stuff. Okay, so custom here is at 0. Let me just sleep. Let me just make sure that this is actually what it is. That might have been too much sleep. Yeah, okay, so custom here has all the time if I do that. So yes, this logging is working. When you add slices like we have here, it's not any overhead. So I need to check for copy, eval copy here. Yes, so with, let's just do custom. Let's just do this. I want to see how much overhead this is. Profile.custom. Okay, so this custom is only taking 2% compute. So there is overhead here somewhere that I do not know where it is. It's got to be in here, right? Okay, custom is about 7%. It's about half of the copy time, 8% of the copy, half of the copy time, a little more. This store function is. So where's the other half come from? So far, I can't find anywhere else that's even 1% of the total copy here. Eval forward, right? Eval copy. Maybe it's the fact that there's, oops. Maybe it's the fact that there's no synchronize on here. Could that be it? I do this. Okay, so this is 2% right here. Still doesn't add up. This is 2% right here. 3%, okay. So this assignment actually does cost something. It's a slice. That's hard. The issue here, right, is that if you always get the NVIDs in order, then this is fine. If you don't, there's a problem. And if you don't, there's a problem. So we are at the point where fancy indexing is one of, if not the main bottlenecks. So we know now we have about 5% if we can figure out LSTM state management. We can get about 5% performance back. And then with eval copy here, this is about 8% performance in store. Is there anything we can do to optimize store? Let's see. Non-blocking equals true. Let me make sure that the thing I'm planning on doing here is safe. I think it is. Mutating the original copy. When it transfers from GPU to CPU, there's no guarantee that the data read on GPU is valid. So 2 CUDA, and then this is CUDA to CPU. Also fails to produce reliable output without synchronization. Okay, so you actually have to synchronize here as well. Left. So I think what we do here Let me make sure I have all of these. Actually, let's make sure that the thing is the bottleneck that I think it is, right? Let me make sure that this is actually, we'll just do profile. I did already, it was a piece of garbage. That trace profile fucking sucks, man. It's so heavy. Okay, 5% leaking here. So I had an idea for this. I think we can async all these transfers if we're careful. Do non-blocking equals true, but then you have to be careful. We do. What does Torch RL guy? He just batches. It kind of does what this is I'm doing here. Kind of does what I'm doing here. Actions of indices. So these are already on the right device. Why do I take them all off of the device? I don't actually know. We should look at that. But we're going to do this iteratively. Yeah, but mind you, so there are some tricks we can use in LeanRL. The main one is we're not compiling it all. So they're three times faster than CleanRL without compiling. We are 30 times faster than CleanRL without compiling. But there are still some tricks here. Okay, cool. So now we have to do torch.cuda.synchronize obs. Okay, so obs value mean. Does this do anything? Why does .cpu not take doesn't .cpu, it should take That should take non-blocking, right? Yeah, there is. And for some reason, you can't do non-blocking on .cpu, but you can do it on the device. You should still have a .cpu that's an alias. Okay, so that actually does help. We just got back a couple percent from that async. Pretty small optimization, but it is an optimization. Back to gift making. Good luck. See ya. How much are we losing from this sort? Oh yeah, we're losing, or this extend, we're losing a lot. Okay. Really, just from this one operation? Okay. Let's figure out this piece of code here. Okay, that's 0. Okay, so this is 4% right here, right? 5%. Still 5%. Is the append, env key, start plus I, and step. Huh. That's funny, but yeah, that's totally legit. Python's just really slow. Let me think how to do something about this. NumPy array, maybe? You can't pre-allocate the sort keys. Well, you can pre-allocate storage for them, but you don't know. Hang on. It's not. It's just Python's being crap. Is all it is. Hold on. I think we can do it as a NumPy array, so we can allocate the storage, but I don't. It's not the storage that's the issue. It's the iteration. And setting NumPy arrays is also slow. Let me try. Let me see one other thing here before I go into this too much. So because there's a second problem. Okay, yeah, that's it. 17%. Yeah, we can get rid of that. That's crazy. You know, this was very, very efficient when PufferLib was training at 100,000 steps per second, but not so much when you're training at 1,000,000. Holy. Do self.sort keys. So you collect data. The order you collect data in is not predictable because we have asynchronous simulation. So this is used to tell you, essentially to figure out how to sort all the data so that you can train on it in the correct order. Oh, hold on, that doesn't. The way I did this doesn't make sense, does it? Pointer, colon, end. Maybe it does. Yeah, no, this is good. This works. And then sort. There it goes. Sort key dot get item. And actually, we can do indices. Uh-oh. How'd that happen? 31's at the bottom. There we go. But there should not be multiple zeros like that either. Yeah, there should not be multiple zeros. Oh, is it sorting the rows separately? Yes, probably sorting these separately. Array to argsort. That's wrong. Maybe this. There it is. So this is a mess. Oh, but this is correct. It is correct. It's a mess, but it's correct. So we will see. We'll probably want to do this so we can eliminate the cast. But let's... Okay, that broke terminal. Okay, that is slower. That is slower. If I just do IX equals sort. If I just do this, let me see if this is faster. Oh yeah. So it's all coming from this one sort line, which is great because we just have to figure out how to make this fast. Yeah, so this doesn't work. So I need to sort by multiple columns. Yeah, this is slow. Nope. Four. Columns. Sort rows. Let's try this. Well, this is freaking wrong, so that doesn't help me now, does it? This is fiddly, but there's 30% perf on the table here. Yeah, that's bizarre. Gotta be a better way of doing this, right? Oh, okay, hold on. Yeah, hold on. There it is. But how is it that range sort keys? Is that right? Hang on. Seems right. Okay, this is one thing that we've gotten. Yeah, okay, so this is correct. I'm a little confused as to how this works because you think, make sure you sort by let's sort keys star 1, sort keys star 2. That's really weird. No, this isn't. Sort by. Sort first by surname, then by name. Oh, so it is actually, the interface to this is just backwards. Okay. I'm not crazy, it's just that the interface to this thing is backwards. Cool. Yeah, that's totally fine. So do equals sort. 1.4 mil. Beautiful. 1.4 million, just like that. Do you think Raylib will be sufficient? Of course. Why wouldn't it be? Raylib's great. Have you seen their Pygame interface? It's literally just, I mean, you can decide whether you want to do like a snazzy 3D one or not, but this is their Pygame interface. Well, this isn't even their Pygame interface. Their Pygame interface is 2D. Where is it? Cool. So we're up here like 30% already. There's still a fair bit of overhead I'm seeing. And we haven't even touched compile yet. Let me use the restroom real quick. I'll be back in a minute. And then we'll keep looking for more stuff to fix. Cool. What happened to my my screen? Somebody moved this on me. We're sitting at half of time and forward. It's a lot. At least a good chunk of that is copy overhead, though. Let's see. Let me see if I can figure out how much of this is. And then profile.custom. We want to get rid of this. We want to get rid of this. Okay, make sure this is the same. Okay, so custom is still tiny here. Okay, this is 5% right here. So yeah, this is 5% compute on doing nothing, I think. 6% compute. I can only assume, hang on, if it's 6% compute doing nothing, Because this is the only other stuff, right? Oh no, this is... Really? That's the 6%? Hang on. How much is right here? %2. Torch.as tensor .2config.device. That's got to be it right there, right? That's 2% is moving the obs onto the GPU. That's actually pretty reasonable. That's pretty reasonable. Okay. You forgot the synchronize call. So that's not going to work. Put that there. Put that there. Okay. About 4% right now, leaking just on this LSTM assignment. It's annoying. It's very annoying. I mean, that is a single copy, right? Like, this is with slicing. Why is that so much? Right? I mean, that's not nothing. That's like... I'm trying to think if there's anything I can remotely do to fix that. I don't think so, not without breaking the async setup I have. Apparently somebody reset that. Not without breaking async. But at least we're only leaking 4% now, not 7. Okay, so that is 4% of it. What about the rest of this copy? There's still like stuff we're not getting, right? Eval copy. Oops. Okay, here's something. Store is now 2%. So where's the rest of it coming from? Did I miss something here? Still 11%. Okay. If I do this, does it close the gap? No. Kind of. I think there's a very small optimization we can do. Very small optimization we can do right here. We're going to clean this all up after. We just need to make sure we get the perf. Okay, so now this way more closely tracks this. This tensor mask. There we go. Okay. So you profile eval copy, profile eval forward, you profile eval copy. Now we still have 15% overhead. %0. Okay. %0. It's gotta come from somewhere, doesn't it? So there's 4% compute leaking. And I'm being told that none of it's from here. Can't possibly be from this. No. Ah. This is where the compute is, huh? Okay. How is this possibly where the compute is? That's so funny. That's 3% compute saved. Literally just by replacing sum with a NumPy sum. Cool. Well, we're at 1.5 million steps per second, which I think is pretty damn cool. That's up more than 50% since we started. That's a heck of a thing to be doing. Let's run this now. Okay, 0% miss. Already got to 1.5. What did I miss? Just a lot of fiddly debugging. Main things are there's some stuff that we're doing with indexing. There are some asynchronous device transfers. The really big one was the way that we were sorting training data was slow. And then I just found like a random sum. Increase speed here like crazy. Yeah. I just haven't done this in many months since like Puffer was way slower. And every time you get faster, right, like new stuff ends up being the bottleneck. So stuff that didn't matter to optimize before matters now. Moving sort to NumPy, yeah. Well, it was just it was a Python list before, which it doesn't matter when it's 100,000 things. It matters when it's 1,000,000 things per second. Literally, like just to give you an idea of how fast we're going here, I just replaced sum of duns with duns.sum, and I just got a 3% speed up. I guess that sum loops in Python and NumPy loops in C. So, we're at the point where really small stuff matters a lot. Because Python will, Python actually caps out at a surprisingly low number of iterations per second. Like, if you write a really simple program in Python, you're going to be capped at like low tens of millions of iterations per second. Python's just really slow. So, tens of millions, if you get like 10 million steps per second, right? If you have one of those operations in a 1,000,000 step per second program, that's 5% overhead. And we'll fix that later. Don't worry about that one. Train has a MISC as well. Compute JE. And flatten batch. Profile dot. Wow, I don't know if I want to look at this one just yet. Let me think what else there is to look at here. Copy. What do you think about TinyGrad? Cool project. Very cool project. He's right. PyTorch is very bloated. They're not doing the eager mode, which is kind of annoying. It's like all graph compiled, so it's closer to JAX or something. Without JAX is like god awful syntax for the most part, it seems. But yeah, it seems fine. Probably the next thing to look at is going to be if there's anything in forward that shouldn't be there. No, forward is just forward. So 52% of the time is in here, huh? Oh no, there's more stuff in forward. Hold on. Custom. With profile.custom. Synchronize. How much does this take? 8%. 8% is sampling logits. Okay, let me see if I see anything weird in here that looks like it could be made faster. Torch.multinomial. Yeah, but these list comprehensions are list comprehensions over like one thing or like a few things. Hang on, I just heard. Let me just see what the hell that was. Hello? Did I hear something? Okay. What's the TV? What's this line take up? Objects. The heck? Oh yeah. It's only, that's 4%. So about half of that came from the multinomial. When a sample index is drawn for a row, it cannot be drawn again for that row. Wait, what? Okay. Is that 1% faster? No, it's not. It's the same. Okay, I was wondering if this would be slow with replacement or whatever. Out equals. Bounding value hierarchy seems. Well, check if you actually need to do it first before you just naively port stuff, right? Like, does the thing you do, does the algorithm or whatever, does the way he's constructing it make sense? Is there a simpler thing that you can do because everything's not on crazy GPU land? Oh, also, you don't even have to implement that thing first, right? Like, you can get the whole thing working end to end, just like checking every object, right? So it's quadratic, and then you can like add optimizations from there. That's probably smarter. Yeah, exactly. So just like, go like do the simple thing first. And I gotta help you with the data structures as well, but I'm doing this at the moment. I mean, I figure if I can spend a day and get the thing to be more than 50% faster, that's probably going to be pretty darn good. Hang on. Categorical. Any guesses from what I've done before on timing to get something decent with your DS help? I mean, whenever you need help, I can help. Do you have like an understanding of the GPU drive architecture and everything already? What's this multinomial do? I'm kind of confused. how long it'll take me to port. High level, I think I understand. Details, still reading through. I mean, it depends how much of the stuff you add, right? Like the level editor is going to take a while. A lot of things are going to take a while, but like I don't know. I think I could probably knock something like basic together in a few days that kind of looks like a driving sim. Um, it really depends how much of the stuff that you add that is in there. Samples elements given tensor based on. Yeah, I don't remember this being PR'd to PufferLib as like a perf enhancement, but I'm looking at this thing and it's not actually doing multiple like multi-discrete actions at the same time. So something's weird with this. First input being tensor. Tensor to sample from. Well, here it's sampling indices. Like you're not sampling from something, right? You have a distribution and then you're picking the index. That's the sample. Logits to probs. Ah, so this uses multinomial. So we just skip this and we go use multinomial directly. Okay. So then this is fine. Logits.log prob. Oh no, wait, hold on. Is discrete. Getting something that renders the Waymo set should be relatively easy. Yeah. interesting that there's 8% in here. Yeah, there's like 8% in here. This thing just need more ends. Okay. Yeah, that, interesting. I mean, I can go like 16. The training forward pass. I'm trying to figure something out. 32. Here's what I'm trying to figure out. Forward pass of the train routine is 14%. Okay. And in my case, it's 54%. So what's different? Stuff to go through the network. Just make sure it's not like all of a sudden exploding. No, actually it's lower than before. Okay, so there's, for some reason, there's this massive gap. I'm trying to figure out what it would be. Use decode action. Unless the train profiler is wrong. Maybe the train profiler is wrong. Let's see about that. No. Train profiler is consistent. Encode decode sample is 14%. Maybe there is something about the batch size. Because this goes in as 2048. This goes in as a sequence. This might be an LSTM thing. Hang on. Reading through his stuff this weekend. Just ping me. Yep. Pretty much. Yeah, so without the LSTM here, tiny little model trains at 3.2 million steps per second. And then look at that, the forward time is way closer to the forward time in, yeah, the forward time is way closer. Okay. 6.3. And now, is there scaling here? If I do 8182, do we do 21%? There's a little bit of scaling above 8192, it looks like. Okay, and then 32K. So there's definitely something going on with the RNN here. 51% forward time. Goes up even a little more with more M's. We see this, right, though? So forward takes 3 times longer than train with the LSTM. Without the LSTM, they're roughly even. I'll be right back. Give me a minute, and then we'll figure this out. right. I'm trying to think now. What could this be? Right? Just the forward pass. Eval forward. Now we do have this stuff in the middle. Fine. Now there's no reason that this can't go higher, right? If we do this. Can I put this up here? Copy. And then if I do that, I can delete this line, right? Which also means I can delete this line. So now we don't have the synchronizes in there. Does that do anything? Not much, really. Let's make sure I don't have stray decorators. No, that is correct. Okay. That's got to be a synchronized bug, right? Yeah, it's a synchronized bug. Holy. Okay. So all the time is in this function right here. Also, you're a moron. You put your LSTM stuff completely wrong. But now we figured out that it is profile, so with profile custom. Here we go. %. Half of my time is going into the policy encode. Only 14% is going into it in training. Is there something screwy going on? It is an int 8. But it should be int 8 for both of these, right? Let's make sure. Yep, it's int 8. So that is not it. That's so weird. It's very weird. Okay, I have an idea. Let's just profile via LSTM call. Well, something double counted, right? Yeah, that double counted. Okay, so 40%, 45%, 6% in here. And that's including the other forward call. So yeah, all the time it's just happening in the LSTM. Empty. Sup, Doc? Hey, how's it going? We are making some big gains in optimization here. I wonder if this thing doesn't contain a cell, does it? If we look at the LSTM, forward. Okay, hold on, look, there's something here. So if it is a packed sequence, you do some stuff. Otherwise, do I do .train.eval? No, I don't. I don't even bother with that stuff. It should be freaking faster in forward than backward mode. Now that doesn't fix it. Same speed without no grad on this. Okay. It's very weird the way that this is. So if you don't pass it, it just makes zeros for you. Jeez, PyTorch, you're not fun to debug through, are you? Hmm. I'm trying to think how we can determine why this is happening, because this is definitely the biggest spot for perf at the moment, is I don't know why the LSTM is 3x slower, at least 3 times slower in inference versus training. fine. Maybe there's some pre-processing that's done that's like really slow. Let me see. So here's our LSTM, right? And where's the call to this? So when you call forward on this, here it is. Update flat weights. I don't know why that's called. Okay. We're not giving it a packed sequence. Input dim. Okay. Is batched. We gave it batched input. This doesn't get called. Is batched. We get this. This is fine. Permute hidden. Sorted indices. Wait, each permute indices with sorted indices. Sorted indices is none, unsorted indices is none. Huh? What? Oh, okay, so this just gets called. Fine, permute hidden. Where's permute hidden? Yeah, they are always none. That's why I was wondering why they were there. Def permute hidden. Apply permutation. Index select. Dim permutation. Okay. I think I actually have to go to the freaking torch profiler again. And how obnoxious this thing is. Let's see if there's a simpler one, since I really just need to time this one function. Whoops. good. Try this. Model inference. Okay, so here we get the 10 LSTM is for inference, usually very high. This one's weird. QDNN RNN. Inference 100. So what is A10 LSTM doing? QDNN RNN is slower. Running a torch profile and LSTM 6. Yeah, you can see it here. It's this. I don't know what this function is though. Native PyTorch implementation, which is a fallback. Okay. Well, we do have QDNN. This is getting called still. This is very weird. So this is still getting called. Here. 2, 3, 6. Okay. Oh, hold on. Millisecond. This is the first call, so this takes longer. And now it's at 300. And now it's at 300 still. Okay. 400. This one went fast. This one. That might be the last batch or something. This one, and then 650. With one exception here, right? These are all at 650. It's much lower here. Why do I see 2 on C both? Was that 16? Doesn't strictly choose one backend. So this is the high level one. So, okay, this is overhead then. Tuning is optimized for longer sequences. No, see, the thing is, we're still getting the same time. I think that there's some reshape operation or some bullshit happening in the LSTM implementation. Where do we get the source. Where's A10 LSTM? Vulcan? State output. Is this it? Oh, you are giving it way more data actually on the hidden state, aren't you? That makes sense. Maybe it is 3x slower because you're giving it, instead of just input, you're giving it input and then two different hidden states. Okay. But then the setup cost should be 3x, not 6x, right? Is it 3x or 6x? It's more than 3x. I think there is a functional LSTM, right? No, there isn't. It just made that shit up. Dang it. I think how we can reduce that overhead. Batch first, drop out. Nice. Okay. And you input this. It's very difficult to know where this is coming from. No. RNN relu, RNN tanh. Be LSTM. RNN relu. Okay, so there is a separate function here. Hmm. Maybe we can compile it, I don't know. Commented that. Come on. And let's comment these as well. See what they do with these coup de graphs. Coup de graph module. Oh. Doesn't do anything, right? I don't know if it's working correctly. I think this is separate, though, from the LSTM problem. I don't think what we can do about this. LSTM going crazy. This is tough. I mean, we need LSTMs. GRU only has one state. Does GRU have, hold on. Yeah, only has one state. That would be faster, I would think. I have this thing set up for LSTMs, the problem. Okay, here's an idea. Well, no, even if I pass none, it's still not going to work, right? You know, the issue is... You would think this would be made up for, though. What the heck does the A10 LSTM even do? I don't know what the overhead is. The problem. I'm gonna think about this for a bit. Might want to go get some lunch. This is solid progress. We are already up more than 50%. So I'm gonna get some food. I'll be back. And then I think we'll probably mess with torch compile a little bit first just to see if that evens out the numbers. Because it's like overhead anyways. So maybe compile bypasses it. We'll see. I'm gonna go do that. And I will be back.